Hello and welcome to another Conifer Electronics video. In this video, we are going to provide a company overview for Conifer Electronics. We'll introduce our company to you and present the design challenge which we aim to solve, the tool suite which we have developed for that purpose, the design flow using the tools from our tool suite, and the benefits of applying this design flow compared to state-of-the-art approaches. So let's begin. Conifer Electronics was founded in 2025 with the purpose of creating EDA tools for integrated circuit design, especially for high-frequency applications. Our mission is to deliver design tools which replace manual matching network design in a similar way as digital synthesis tools replace manual design of digital circuits on gate level. We offer a platform for synthesis of basic building blocks of RF integrated circuits such as inductors, transformers, and balance, as well as for synthesis of more complex multi-element structures such as matching networks. Our platform is based on reusable tool infrastructure that can serve multiple projects and designers within same technology. Our team brings more than 14 years of experience in the semiconductor industry, especially in the RFIC design. Thus, common design challenges which are encountered in RFIC design are well known to us. The key challenge in RFIC design is the design of matching networks. Now, why is this so important? Matching networks dominate the RFIC performance area and the design iteration time. This becomes clearly visible if we compare the design of matching network to the design of active circuits, that is transistors within the RFIC. Transistor design is much more straightforward. The size of a transistor is set by total current and current density IDS over W, with one current density being optimal for low noise and another being optimal for maximum oscillation frequency. Knowing this, reusable building blocks can be organized as a small library of unit cells. There are only a few main topologies must be covered, mainly common source and common gate. On the other hand, setting of matching network parameters depends on topology, frequency, bandwidth, and adjacent stages. Matching networks dominate chip area and strongly affect efficiency and gain, thus directly impacting both performance and cost of the RF integrated circuit. Their performance is very sensitive to real implementation details and quality factors of passive components which are used to build them. They are much harder to design and are usually unique for each circuit. The existing design flows for matching network design have significant shortcomings. One of the key issues is that generally foundry PDKs contain only very few passive component models for working with high-frequency RFICs. Another key issue is that designers still rely on manual topology choices and repeated layout plus electromagnetic simulation loops. This can lead to a large number of design iterations. As electromagnetic simulation has to be repeated for each design iteration, this iteration time represents a significant chunk of total design time, which is a serious limitation of the existing flows. Another limitation is that the design result is strongly dependent on designer's expertise. Also, at very high frequencies, the best performance can be achieved by transformer-based matching networks. But for this matching network type, there is only weak support by existing tools. So, what would be needed for a successful design of matching networks? First, on-chip friendly matching network topologies with easy biasing should be applied. Also, matching network synthesis should be based on realistic component models instead of ideal lumped elements. Otherwise, the design might be suboptimal or the design process might have too many unnecessary iterations. Additionally, reusable libraries with parametric components and native transformer support should be available. We aim to solve these issues and overcome the limitations of the existing design flows by our tool suite. The Conifer tool suite for RFIC design consists of 3 tools: MCell, MMod, and MRF. The first tool, MCell, generates DRC clean layouts for custom passive components such as inductors, transformers, balance, and T-coils. To characterize these components, an external electromagnetic simulation currently has to be used as a supporting step. The second tool, MMod, fits electrical network data derived from an electromagnetic simulation into proprietary models called M-models, which are specifically adapted for fast reuse during synthesis. Finally, the third tool, MRF, synthesizes matching networks from a set of requirements using real passive component models instead of ideal elements. Now, let's take a look to how these tools are used within the design flow. The first stage in the design flow is library synthesis, and it is based on our MCell and MMod tools. It starts with using MCell for generation of DRC clean layouts of custom passive components. Then the electromagnetic simulation of sample geometries generated in MCell is performed in order to obtain network parameters for these geometries. These network parameters are then used as an input to MMod in order to extract M-models of passive components. The result is a reusable passive library. The second stage is matching network synthesis, and it is based on our MRF tool. MRF takes design specification in form of Tcl script as an input, uses the reusable passive library generated by MMod, and performs an optimization, that is, a topology and value search to find candidate matching networks satisfying the design specification. In the end, electromagnetic verification and fine-tuning are performed. We can see that the expensive step of electromagnetic simulation is shifted into reusable library creation instead of being repeated in multiple iterations for each RF block. This is a major speed up. Once the library exists, designers can specify requirements and synthesize candidate networks quickly. Let's see what's changing from the designer's point of view when switching from the conventional design flow to Conifer design flow. In the conventional flow, the starting point and topology selection are done manually. The layout generation and the electromagnetic simulation remain inside the optimization loop, making the design iterations very slow. This is done separately in every project, so each new project repeats much of the same exploration effort. Also, final design quality strongly depends on the expertise of the individual designer. On the other hand, in the Conifer design flow, passive libraries are synthesized only once for each technology used. As electromagnetic simulations are done during library synthesis, and the library is reused during matching network optimization process without repeating these simulations, the electromagnetic simulation effort is significantly reduced. The matching network requirements are specified in a simple script, and the synthesis is automated. The automation of synthesis is done by using real component models. So we can see that using the Conifer design flow brings a lot of benefits. It provides design space exploration, which is orders of magnitude faster than optimization based on repeated electromagnetic simulation in each iteration loop. Real component model-based synthesis improves relevance for silicon implementation and helps avoid reiterations after final electromagnetic verification. The Conifer design flow is a strong fit for transformer-based and other integration-suitable matching networks. It lowers the barrier of expertise needed for a matching network design and enables designers who are not matching network specialists to quickly deliver near-optimal solutions. And finally, besides delivering near-optimal solutions, the flow is kept reusable across projects. In further videos, we will provide more details regarding each of our tools. For more information, you can also visit our webpage www.coniferelectronics.com or contact us at info@coniferelectronics.com. Thank you for watching this video.